Hello, good morning everybody. I'm glad some of you survived the party. It looks like it lasts long. So we are here for another wonderful day of interesting sessions, and now I leave the word to Chiara Di Francesco Marino from FBK in Trento, and she will talk about predictive process monitoring, on which she has been working long about. Okay, thank you.
Thank you, Massimiliano. Thanks a lot. So good morning, everybody. And this session was assumed to be presented by myself and Chiara Ghidini, but unfortunately she couldn't be here today, so you have to listen to me for 1 hour and a half. So this session is about predictive process monitoring. So what is predictive process monitoring? Well, predictive process monitoring deals with predicting the future of ongoing execution. So what will happen in the future to our ongoing executions? And this is somehow the outline that I would like to present today. I would give a very short introduction to what predictive process monitoring is. And then we will have a look at predictive process monitoring by looking at it from 3 main dimensions, and then we'll take one of these dimensions and we will look a bit more in detail at these dimensions, at the pipeline related to this dimension. And then we will see an overview of new trends in, let's say, these new trends of predictive process monitoring, or if you want, a new trend in machine learning-based operational support, and then we will see at the end some tool support. So let's start with the introduction to predictive process monitoring. So just to place a bit how predictive process monitoring is placed with respect to process mining. You may have seen in these days that we have in process mining 2 types of data. We have post-mortem event data and pre-mortem event data. Well, the post-mortem event data refers to cases, to executions that have already completed, and then that cannot be modified anymore. While pre-mortem event data refer to cases that are still ongoing, still running, that are still alive, and so we still can do something with these executions that are ongoing. So I think that many of the sessions you have attended in these days have been related to this post-mortem data. So, like for instance, the discovery is related to data that are already concluded. While operational support is this part of process mining that focuses instead on pre-mortem data. So, for instance, and that support me making decisions on executions that are ongoing, on cases that are ongoing. So for instance, if you look at these execution trees here, we can think this as the history of a patient, let's say John. So John is registered at the hospital at 8 a.m. He is visited at 8:15, and now at 8:54, well, I was almost precise with the time. Let's assume that now is 8:54. Yes, he's going to perform X-ray. So this is the past and the present of John's history that we know, but we don't know what will happen in the future. So of this execution, we know the past and the present, but we do not know the future. Well, what can we do now with this ongoing execution? Well, one thing that we can do is we can detect if something went wrong. So if what the X-ray that we are performing now is something that shouldn't happen. We can predict what will happen to John in the future. So we can look at the future of John. And we can also recommend something to John in order to achieve a certain objective or a certain goal. So these are, let's say, the 3 activities that in the big picture of process mining, operational support, which is this part of process mining that deals with pre-mortem data, so data that are ongoing, you can carry on. And what we will focus on today is more on the prediction part, and we will see something about the recommendation part. So what is predict? Well, whenever we use our information systems, you may have seen we collect a lot of historical data that we can store. And this historical data can be used in order to train a model. And this model can then, at runtime, when John's history is being executed, can be queried by the operational support system in order to provide predictions about the future of John's execution, and then return these predictions to the user. Okay, so let me say it in other words. What is predictive process monitoring? Well, predictive process monitoring takes as input a set of historical traces, an event log, a set of post-mortem event data, and an ongoing trace, so a trace that is still running, and it returns a prediction on the future of this ongoing trace. Or if you want, given a prediction problem, like for instance, whether John will recover soon or not, and given a set of historical traces, so again, post-mortem event data, predictive process monitoring techniques builds a model, and so that at runtime, when we have John's history, John's trace going on, it will return the prediction. Okay. And this concludes the first, the overall introduction. I hope that everything is clear of this thing, on this thing. Okay, now let's try to focus, to look at predictive process monitoring along 3 main dimensions that help us also to somehow classify the predictive process monitoring state-of-the-art approach, to classify this state-of-the-art approach of predictive process monitoring. So, what are these 3 dimensions? Okay, the first dimension is what we want to predict. So the type of prediction that we want to return. So for instance, we can predict an outcome, which can be, for instance, the outcome of our John's ongoing execution. So for instance, will John recover soon? We can predict a number when John is going to recover, or we can predict sequences of next activities that John is going to do. But we will see it later. The second dimension is what kind of information we are going to use in order to make predictions. So we can use only the control flow, so the sequence of activities of our data. We can take into account also the data payload associated to this sequence of activities. And we can also consider some unstructured information, some textual information, or we can also take into account some contextual information. And the third dimension is instead related to how we are going to make these predictions. And we can classify current state-of-the-art approaches on predictive process monitoring in 2 big families. The ones that work with an explicit process model, and the ones that instead use machine learning or deep learning techniques in order to make predictions. Let's have a look a bit more in detail at each of these 3 dimensions. Let's start from the dimension 1. So what do we want to predict? And let's look again at our John's history. And now we have, I think, an activity more. So he registered at 8, he go to the radiology department at 8:10, and he get the visit at 8:15, and then at 8:54 performs X-ray. What we can ask ourselves, or what we can ask to predictive process monitoring about the future of John? Well, for instance, we can ask some questions like whether John will need some ultrasound. So this is a question that we can classify as an outcome-based prediction, in the sense that the answer to this question will be a kind of categorical value. Yes, no, true, false, or a categorical value. Another question that we can, and in this case the answer, if our predictive process monitoring returns a correct answer, will be yes, because we can see that in the future John is going to perform ultrasound. We can also ask when John is going to have ultrasound, and we can classify this as a numerical prediction, in the sense that the answer to this question is actually a number, which can be, for instance, in this case, at 9:20 p.m. But we can also ask to our predictive process monitoring techniques what John is going to do now on. So what are the sequence of activities that John is going to perform from now on in the future? Okay, so this is the first dimension, and then we will look at a bit more in detail using these 3 dimensions at the different pipelines. Okay, let's move to the second dimension. What I mean when I say what kind of information we can use? Well, we said, okay, we can use the control flow, so just the sequence of activities of our execution traces. Or we can use also the data associated to the events, the data payload. So, for instance, the timestamp, but also, I don't know, the resource who carried out the activity or whatever other kind of data payload. Sometimes we can have some unstructured information, some textual information also available. And so sometimes you can use also some textual information for helping your prediction, your predictive process monitoring approach to make predictions. And finally, we can also use sometimes some contextual information. So for instance, when John is going to perform X-ray, maybe it can be available some information about whether a certain scan machine is free or not. So these are the different types of input that we can use, and today we will focus especially on the control flow and on the data payload. Okay, let's move on, the third dimension. So what kind of approach we are going to use to make predictions? Well, in general, predictive process monitoring approaches work in a way that we have two phases. We have a training phase in which we learn from an event log a model. And then at runtime, when we have our ongoing trace, we have a second phase, which is the runtime phase. When we have our ongoing execution, we can query this model in order to get a prediction. And we can say that, as I anticipated before, there exist two big families. One is the family of the model-based approach. In this family, we have actually a kind of an explicit representation of the process model. We can say that the main characteristic of the model-based approach is that you have a kind of an explicit process model. You can see the process model. And usually you enrich it with different types of informations that help then you to get the prediction. And we have instead the family of supervised learning approaches in which you usually use machine learning or deep learning techniques. And in this case, you do not have an explicit, you have just an implicit process model, but you do not see the states or the steps of your process model. It's a machine learning model, so it's a different kind of model. And we will mainly look at supervised learning approaches in this session, but I would like to give you a brief idea about also the model-based approach. So I will first go through to give you the idea of the model-based approach. So how does the model-based approach? Oh, first of all, there are questions so far. Please. So you are saying if we train the data, we train the model before with some post-mortem data, so with data that are completed, and we train our model. And then when you have an execution which is incomplete, you are going to query your model, and you are going to predict some delay. So you learn from the past, let's say, what has happened in the past, and you predict what will happen to a new case which has a similar behavior to some behavior that you have observed in the past. Yeah. This is for the part of recommendation, and that's true, but for the part of prediction, that's also true. But of course, maybe also your ongoing execution is an execution that will be late, and so you want to predict that it will be late in order to take an action in case to recommend an action to avoid to be late. But you should learn also from your errors. So if you observe some errors in the past, you need to be able to predict that also your ongoing execution will be late, so that maybe then you can take an action. Okay? And the second question? Okay, when you get, okay, this part was more focused on predictions, but when you make, okay, of course you can make a wrong recommendation, but especially if you are dealing with, let's say, hospital things, these are just suggestions, and of course the doctor has to, I mean, of course you cannot take these techniques and give them to the doctors and say, okay, now you apply it and don't think anymore. So of course there could be errors, and so in that case it is important that the doctor has his own view on that. Okay, okay.
I have a question about the pre-mortem and post-mortem concept, in which, what about the event log? How the event log will be generated in the pre-mortem and post-mortem technique? So what I get is like that there is a process going on, and we are dealing with the process in a real time. At a moment we are seeing the pattern of the past behavior of the process and what is the behavior now, and we stop the process there, and we will predict the next events based on the previous history. So what kind of event log will be there? It will be continuous, stored in the form of table, or what?
Okay. I mean, it could be whatever kind of form, actually, your ongoing execution. It's just, I mean, the important thing is that, as you said, you stop the execution You are at that point in time, and you stop there, and you make a prediction on that execution. The important thing is that you collect the information. Then if it can also be an event log with just one trace, and from when the patient entered, for instance, just to keep this example, if the history you are looking at are the history of patients starting from when they enter in the hospital, you take the history of your ongoing patient from when he or she entered in the hospital up to now.
Like if there is a big hospital, for example, and there are many patients at the same time, and they are and it is the same event of process patterns, then is it easy to manage all of the patients at the same time and to store information and to predict individually, like what will be the next, what is the history. In that manner, we are dealing with a lot of processes at the same time, and I don't know how.
You are dealing with several process executions, but the process possibly is the same one, right? So you're dealing with several process executions, and in this case, with this kind of algorithms, the most consuming part is not making a prediction, which is quite fast, and you can deal it also with several patients because it's kind of very fast. What it takes time is to build the model, that you have to train the model, and so this is the most time-consuming part, and for that thing you need to reserve some time slot. So I don't think, I mean, predictions are very fast when you just query the model. That's very fast. Okay. Okay. So if there are no other questions, I will go ahead. So the model-based approach. So I was telling you there are these two families of approach. Let me just give a quick overview about the model-based approach. So the idea is that you start from historical traces, and you can already have a model that you have discovered, a process model that you have discovered, or you can discover a process model during the training phase. And once you have this model, you enrich it with some information that you extract from the event log. And this is the training part. And then at runtime, when you have your ongoing trace, what you do is you query your enriched model in order to get a prediction. I really give you one example of the simplest example about, and at a very abstract level, of this kind of family of approaches. So usually, let's assume that these traces, sigma 1 to sigma 4, is our event log. that we use for learning an explicit process model that we want to use with this first family of approaches, which are the model-based approach. And let's assume that we have this ongoing trace, which is just given by compute rate and visit patient, and we want to predict what is the remaining cycle time of this execution. So when this execution, what is the remaining time until the end of this execution. So one of these approaches just build the transition system of starting from the event log, so from traces sigma 1 to sigma 4. I won't go into the details of the construction of the transition system. And then we have a kind of an explicit representation of the different steps of our process model. And then what we do is annotating this transition system with the information on the remaining time of our traces. So for instance, if we look at the state where we have visit patient, and we look at the traces that passes through that state, we see that for sigma 1, the remaining time at the time of visit patient is 11 hours, because it's from 7 a.m. to 18 p.m. For sigma 2, we have 8 hours, because it is from 8 a.m. to 16 p.m. And for sigma 4, we have 7 hours. And then we compute the average of all the traces that passes of the remaining time of all the traces that passes for that state. We do the same for all our states. So for instance, also for compute rate, the remaining time is 6 hours. We compute the average, and we do this for all the states. And then when we have our ongoing trace, we see what is the state where we are. For instance, in this case, we are in this state here. And the answer to our question will be, so what is the remaining time? Will be just 4 hours. Because this is, we have learned from past execution what was the average time that it could take before the end of the execution. And so it's really at an abstract level, but I wanted to give you the intuition of this family of approaches. Okay, what about instead the approach based on machine learning or deep learning? Well, in this kind of approach, we have a slightly different pipeline, in the sense that first we extract prefixes from our event log. Once we have extracted the prefixes, we encode these prefixes of the traces into a format which is understandable by our machine learning technique. Then we apply a machine learning technique or a deep learning technique, in general a supervised learning technique. And this is at the training time, what we do with our post-mortem event data. And then at runtime, we have our not yet completed execution trace. We encode also this trace in a format which is understandable by machine learning models, and we query the machine learning model in order to get a prediction. Okay. But why we need to compute the prefixes? So the idea is that, of course, our ongoing trace is an incomplete trace. So if we want to learn the correlations between, if we want to make predictions on the future of our ongoing trace, which is just an ongoing trace, we need to learn correlations among past data, but just prefixes of past data, not complete past data, and what we want to predict. And that's why we need to compute trace prefixes, because we want to teach our model that there exists a correlation between just prefixes of our traces and what we want to predict, and the final outcome of what we want to predict. For instance, between the first two activities and the final outcome of the execution, or the first three activities and the final outcome of the execution. And so, yeah, we start from the event log, and the first step, as you have seen in the pipeline, is computing the prefixes. What prefixes shall we choose? Well, it first of all depends on what is the problem you want to solve. What is the prediction problem that you have in mind? Of course, if you want to predict the final outcome, you do not care too much about what kind of prefix you are considering. You can consider whatever kind of prefix. But of course, if you want to make a prediction at the beginning of your execution, for instance, the time in which an activity, which is usually at the beginning of your execution, occurs, you need to be careful to choose a prefix which happens before that activity is executed. And then it could depend on how early you want to make your predictions. Of course, the earlier, the better. if you are able to make your predictions when you observed only few events, is better because, of course, there is more unknown future that you are able to predict. So in general, what you can do when you train your models, there exist different strategies. One possibility is that you, since also these machine learning techniques usually require vectors of the same size, what you can do, you can also decide to train different predictive models for different prefix length. So you can have one predictive model for prefix length 2, one predictive model for prefix length 3, and so on and so forth. Or you can put all your prefixes all together and having a huge, big model. And in this case, sometimes you need to use some padding to have these vectors of the same size. But we will see these two aspects a bit more later with the bucketing part and with the bucketing part. Okay, so this concludes the introduction about the three dimensions. And now we can, if there are no questions, we can go through the three type of predictions that we have seen before. So the outcomes, the numerical values, and the next events, and look a bit at what are the characteristics of these three types of predictions. So let's start from the prediction of outcomes. So as we said before, we are interested to predict with this kind of prediction, to predict a categorical value, which can be true, false, yes, no, or whatever other kind of categorical value. So this means that the label of our traces, so what we want to learn of our historical trace is a correlation between the execution and the label, which is the categorical value that we want to predict. So when we train our model, we need to have a label which is a categorical value. So what we want to learn actually is a function that, given our log labeled with the final answer for these execution traces in the event log, returns a label, and this label should be as close as possible when we have an ongoing execution. When we query our model with an ongoing execution, this label should be as close as possible to the actual label of the future of John's history. So, for instance, this is the case of questions like, will John need ultrasound? And the answer will be yes. So just you need to remember is that the prediction that we aim at having are predictions which are prediction related to categorical values, and the label that we need to use for training our model need, therefore, to be categorical values. Is it clear, this? Okay. So now, let's go back to our pipeline, the pipeline that we have seen before. Once we have extracted the prefixes, we need to encode our traces in such a format which is understandable by machine learning and deep learning models. But how can we encode the data? Well, the simplest way for encoding data is using a Boolean encoding. What does it mean? So we need to transform our log, so our set of traces plus the label that we want to teach to the model, into a format which is understandable by these machine learning techniques. And usually these are vectors of fixed size. So what can we do? Well, one thing we can do is we can take the alphabet of all the activities that occurs in our log, and we can consider each activity as an item of our vector. And then we can just build a vector in which, for each activity that occurs in the trace, we set the corresponding item to true. And for the activities that do not occur, we set it to false. So for sigma 1 to true, or to 1 and 0, let's say, for simplifying the true and false. So for sigma 1, for instance, visit patient occurs, and so we set the item corresponding to the activity visit patient to 1. Compute rate let's assume that does not occur in that execution, so we set compute rate to 0. Perform ultrasound occurs in trace sigma 1, so we set it to 1, and get payment does not occur, so we set it to 0. What about sigma k, for instance? So in this case, we observe compute rate and get payment. So we will put to 1 compute rate and get payment. And then, of course, we put the label. We use the label for the training part. So, oh, sorry. So we use the label when we encode the trace prefixes for the supervised learning part. Of course, when we have our ongoing execution, we won't have the label because it's exactly what we want to predict. We want to predict the label of our ongoing execution, which is our prediction. Okay, so we have seen this Boolean encoding, which is the simplest one. Okay, what is the problem of this encoding? The problem of this encoding is that we are not caring about how many times we observe an activity. We are just saying an activity occurs or it does not occur. So another more sophisticated way of encoding data, of encoding traces, is to apply this frequency-based encoding. In this case, we do not only observe whether the activity occurs or not, but also we count how many times it occurs. So when we encode with this kind of encoding, what we do is we always use the alphabet, so the set of the activities in order to label the items of our vector. And then instead of just having 0 or 1, we count how many times we observe that activity. So for instance, for sigma 1, we observe visit patient twice, and so we encode it as a 2. Compute rate, never. Perform ultrasound once, and get payment, never. And then we report the label for the training part and not for the runtime part. For sigma k, similarly, we have 2 occurrences of get payment and 1 occurrence of compute rate. So what is now the problem? The problem is that we have not considered at all the sequence of the activities. We are just counting how many times an activity occurs. And we are not observing, whether visit patient occurred at the first position or at the last position or in the middle. So another type of encoding which takes into account the sequence of the data is the simple index encoding. Here, the label of our vector are not the activity names, but rather the position, the activities at position 1, position 2, position h. So here we are assuming that we are looking at data at prefixes of length h. And we encode our data by looking at the activity which occurs at position 1. So for instance, for sigma 1, visit patient. For at position h, perform ultrasound. And similarly for sigma k, so at position 1, compute rate, and at position h, get payment. Okay? So, well, here we have this encoding with also some categorical values, which are visit patient and perform ultrasound and not numerical. And we will see later that it often happens that machine learning methods require numbers, and so we cannot use categorical values, but we need to transform these categorical values into numbers. But we will see later a technique for transforming these kind of categorical values into numbers. Okay, so what we are forgetting with this kind of encoding? We are forgetting that we are not considering at all the event payload. So we are just looking at the activity names and we are not considering the data payload. So what we can do is to have another type of encoding, which is called latest payload. And here, what is the idea? The idea is that this is always our log, in which besides the sequence of activities, we also have a trace attribute, which is the age of the patient. And we have the department, which is an event attribute. So it changes each time we change the event. So for the visit patient, the department is clinic. For perform ultrasound, the department is radiology. How can we take care also of this kind of information? Or we can take care of this information? Well, one possibility is to consider the trace attributes So we can have an item corresponding to age, and then for the event attributes to take only the latest value that that event attributes take. Well, why? It's like if we consider we create a snapshot at the latest event, and we take the latest value that is taken by that event attribute. And so we can, in this case, we will have that age for sigma 1 is 33, and for the department age, and the value of the event attribute department at position age is radiology. And similarly for sigma k. But we now have completely forgotten the sequence of activities because we are focusing only on event data. So now the question is, how can we encode both together? Well, we can have this index latest payload encoding that actually combine simple index encoding and latest payload encoding. So we have both first the trace attributes, then the activities at position 1, at position 2, at position age, and then the value of the event attribute department at position age. So for instance, for sigma 1, the age is 33, the activity at position 1 is visit patient, the activity at position age is perform ultrasound, the value of the event attribute department at position age is radiology. And similarly for sigma k. Okay, still we are missing a last thing, which is, okay, now we are considering both event payload, both activities, both the control flow, both the data payloads, but we are only considering the latest value of our data payloads. We are not considering how the department changes along the different events. And so we have a last encoding, which is the complex index encodings, which take into account also the data flow. So not only the sequence or the sequence of activities, but also the sequence of values of event attributes. And so we don't have only the value of department at position H, but we will have also the value of department at position 1, at position 2, at position 3, and so on and so forth. And so we have a very complex encoding in the sense that it has to take care of, for each, it has to take care of the trace attributes, then of each activity at each position, and then for each event attribute, you need to look at how it evolves along the execution of the process. Okay, and so this is the same for sigma k. Okay, so we have seen, we have extracted the prefixes, we have seen how to encode these prefixes, and now we can apply a machine learning technique. In the case of categorical values, usually you apply classification-based techniques, like for instance, decision tree, random forest, support vector machine. You can apply whatever kind of classification technique. These are the ones that are most used in the literature. And moreover, you can also have some works also have a bucketing phase before the encoding. So after you have computed the prefixes, you can bucket together your traces and then encode them. Why do you want to bucket them? Well, you may want to bucket them because, for instance, you want to cluster together traces which have a similar behavior and then train a model only for that cluster of data. Or you may want to cluster together traces which has the same prefix length and build several models, one for prefix length 2, one for prefix length 3, one for prefix length 4, and so on. And then you encode your traces, and finally you will have several different predictive models. For instance, one for all the prefixes of length 2, of length 3, of length 4. And when you are at runtime and you have your ongoing trace, you first need to identify what is the bucket you need to take into account. For instance, this trace, assuming that we have used the prefix length for making our buckets, this trace has length 3, so we need to query the predictive model related to the bucket of traces that we have built with traces of length 3. So the predictive model of the bucket of prefix size 3. we identify the correct bucket, and we encode the trace, and we query only that specific predictive model, and we get a prediction. Okay, the second type of predictions that we can look at are the numerical predictions. What is here the idea? The idea is that the prediction that we are looking for is a number, usually. And so also the label that we want to learn is a number. So, for instance, we want to answer to the question, when will John need ultrasound? And we want to learn a function such that it, given a log and given John's ongoing execution, it returns a label, which is a number, as I said, which tells us in how many days John is going to be recovered. As you may see now, the label is a number and not anymore. The label that we want to learn is a number and not anymore true, false, or yes, no, or a categorical value. What kind of encoding we can use? Well, we can use exactly the same encodings that we have seen before. The only thing that changes is that in the training phase, the label is a numerical label and not a categorical one. So we can use the Boolean, so we will set 1 or 0 according to whether the activity occurs or not in the execution. We will use the frequency, counting how many times each activity occurs in our trace. We can use the simple index. So we can look at the activity name at each position, the latest payload by looking at the trace attributes and only at the latest value of the event attributes. Or the index latest, which combines simple index and the latest index and the complex index encoding. Okay, and also here, let's say the pipeline is exactly the same. What it can possibly change is the type of techniques that you use, which will be more a regression technique, because you need to look at machine learning techniques that predict numbers. And also in this case, you can bucket your traces so that you have different predictive models. Okay, do you have questions?
Because I think when you consider this kind of prediction, there are some, maybe not in your example here, but usually in the real world, you have directly correlated events that follows one another, and maybe if you make the cut at this moment when one is always like correlated with the other, you would get some kind of leakage there.
Yeah, it could be if you need to indeed explore different prefix lengths in order to be able to avoid this.
But do you have problems with that, or?
Yeah, you could have. Yeah.
Because, so what is the optimal length that from prefix?
Okay, there is no a rule for that. What you can do is, of course, I mean, when you are predicting next activity, you should try to explore the whole sequence until the end, because so that you learn at each position what is the best thing to predict as next position. When you are instead predicting the final outcome, well, you need to take into account, you can use I would say also in that case it would be good to look at all the prefix length and to have at least one model for each prefix length so that you are ready you are prepared to predict any kind of prefix length. But of course, I mean, there is not a general rule. I would suggest that the latest you have the longer you have the prefix length, the better it is. But as you were saying, when you reach very long traces, you won't have enough data for training your model, and so that would be a problem. It of course depends on the data sets that you have. Usually, it often happens that if you need to make a prediction on the latest value, on the final outcome, you can have a look at, let's say, you can imagine that you are at the middle of the execution or at the beginning of the execution, so in the first half of the execution and not later on, I would say. So, but of course, yeah, it could be a problem as you were saying, because for longer traces, yeah, sure.
Thank you. My other question: how does this cope with missing data? So, how does this classification cope with missing data?
Okay. Well, of course, if you have missing data, you can either use a symbol, which is like a padding symbol that you use really as a symbol which is agnostic about. I mean, it does not have any other meaning. So you mean missing data in the training part when you have for a trace, right? In a trace.
Well, in both cases. So when learning and also when applying it to a predictive case you want to predict.
Yeah.
So how does that cope when, for instance, there's missing attributive data? So not events,
but data, yeah. Usually you put anyway a padding, and of course already with the data, the predictions are less accurate than with the activities, but especially when this happens because you have a limited amount of activities, and so it's kind of, you have an alphabet which is a finite alphabet, while for the data, you usually do not have a finite set of possible values that, I mean, for instance, for the department, yes, because these are categorical data and are quite easy to have a fixed number also of categorical data, but for numerical data, for instance, of course, it's more difficult to make predictions. So I would say you can use padding and you can solve the problem. Of course, the accuracy of your results could decrease.
Yes, thank you.
You're welcome.
One of the things that I was wondering about is when you talked about the encoding into vectors, it kind of seems to me that the later on you went, the longer the vector became. So I was wondering if the length of the vector can cause problems in terms of scalability or in terms of training. Because if it doesn't, then I could just encode the entire data payload together with its history and everything like that. But I'm assuming that is not what I want to do.
Yeah, that's true. I mean, you're right. Of course, the length of the vector could increase a lot and then could create problems. Usually for the examples that I've been working on, when you focus only on this kind of complex index encoding, it is still manageable for the BPI challenge, let's say, this is still manageable in a reasonable amount of time. We will see later on just an idea of instead if you want to include, besides this data related to the case you want to predict, also some information related to other cases that are running together with the case you are running now. Well, in that case, of course, you can have an explosion of the information that you want to include, and so you need to be much more careful about how much information you can include. But yeah, you are right. Of course, the complex index encoding is. Well, I think also on the order of hundreds.
Okay. Thank you.
You're welcome.
I had a quick question. Can we use can we transform the problem into an NLP problem and use, for example, sequence transformers to encode it?
Yeah, we will see now how to predict suffixes. Well, this is one of the techniques that is used especially for predicting suffixes, these sequence-to-sequence models. I think you were talking about this, right? Yeah, these sequence-to-sequence. We will see just some hints about this predicting entire suffixes, but this is one solution that is, there are some recent works which are using this for predicting the exact sequence-to-sequence with the recurrent neural networks. We will see something on this.
Okay, thank you.
Okay, thank you.
Hi, I have a question about the index encoding that you mentioned. That basically, will you map each activity name? Yeah, like this one.
Okay, sorry.
Yeah, so visit patient will become 0, perform ultrasound will become 1. I'm not sure how you encode in this way so that the machine learning model can understand.
Do you mean this one or the?
No, yeah, this one is clear for me because you have all the activities names and
Okay.
1 or 0 if it happens or not. But this one is like a sequence, and I'm curious how you could encode that.
Yeah, you mean how to transform this into a numerical format?
Yeah.
Okay,
Yeah.
we will see in just 1 minute.
Okay.
Okay, so sorry for, and then you can tell me if you understood the solution. Okay, if there are no other questions, okay, let's move to just a quick view on the prediction of next events. So here the idea is that we want to predict not just one label, but we want to predict a sequence, a suffix, or about what will happen from now on to John's history, for instance. And how do we usually do this? Well, we usually do it by using some techniques that we will see, these deep learning techniques that was suggesting before one of you. And the idea is that actually you try to predict one step ahead, and then you recursively use that information for moving ahead. So, for instance, you will use. So, what that function means is that you run first. You predict the next event, and then you use the information that you have predicted in order to predict the next event, and so on and so forth recursively. And so we will get predictions which are suffixes, so the sequence of remaining activities and the sequence of event data. And so how to transform categorical values into numerical values? One of the typical approaches that is used is this one hot encoding, which allows you to, well, actually you have an index function which maps your alphabet or all the categorical values into an index, but you do not want to then use that index because you do not want to impose any order on your categorical value. So what you do then, you transform that index into a vector in which only the corresponding index is set to 1 and all the other cases are set to 0. So just to make an example, in this case, visit patient for sigma 1 will be transformed into the one-hot version encoding of that activity. Since the index is 1, will be transformed into a vector in which the first value is set to 1 and all the others are set to 0. For perform ultrasound, whose index in this case, so here we have our alphabet and the index of perform ultrasound is 2, and this will be transformed into a vector in which the second item is 1 and all the others are 0. And similarly for check X-ray, which is 5, you will have 4 zeros, 1, the fifth index will be 1, and then the other will be 0. And so you use this kind of encoding in order to transform categorical values into numerical values without using any order, let's say without imposing any order. And of course, in this case, you are making your vector longer and longer and longer. Okay, and this is for sigma k, the same one-hot encoding. And sometimes for this kind of prediction of suffixes, we want also to include, well, we want to predict both the suffix in terms of the sequence of the next activities, but also maybe the timestamp in which these activities have happened. And so sometimes we use not only the one-hot encoding, but we enrich it with some temporal features, which are, for instance, the time between the previous event and this current event. So this was the first event, so delta 1 is set to 0 because we do not have any previous event. The hour of the day and the week of the day. Why are we including this information, especially the hour of the day and the week of the day? Because of course, if they are business hours or business days or not, in processes, especially business processes, can make the difference. And this is more or less the idea of this one-hot encoding enriched with some temporal features for predicting suffixes and also suffixes of event data. Okay, and usually here you use deep learning techniques, which are also used in natural language processing, and which are usually these LSTM neural networks, which are recurrent neural networks, which have both a short-term and a long-term memory. But I won't go here into details. Before moving to the next part, I would like to say one thing about evaluation. How we can evaluate this kind of predictive process monitoring techniques? Well, usually an important dimension, as you may have seen in this kind of data, is time. So usually what happens is that we need to take care about the time also when we make the evaluation. And it usually happens that we split our data set in training and testing by first chronologically ordering our data set, the traces in our data set. This is how it is usually done. Why? Well, because the idea is that in this way, we are as close as possible to a real-world situation in which you have post-mortem data up to a certain point, and this is the post-mortem data that you use for train your model. And from there on, you are going to use the ongoing new executions in order to make predictions. And then, of course, the training set and the validation set, so the data that you use for instance, for tuning the hyperparameters of your machine learning techniques can be executed in the first part. And this is particularly important in the cases in which you have so-called concept drifts in your data. So if there are changes in your process or changes in the distribution of your data, of course, you train a model with the old data, and you need to see how that model trained on data, on old data, perform on the actually new data. And the only thing I want to say, there is also, some works which really take a point in the timeline, a precise point in the timeline, and they clearly separate the training from the test set from that point on. But also there, especially you are considering also, let's say you are counting the distribution of your data. You need to be very careful if you do like that, because either you cut away all the incomplete traces at that point and you don't use them in the training set, but this can change, of course, the distribution of the latest part of what you learn in the latest part of your training set, and also the distribution, and if you trash everything which is ongoing when it starts your test set, also there you can have a change in the distribution of the data. So if in your encoding you are using some, let's say, features that take into account also the distribution of the data, you need to be careful about this strict order cut in your data set between training and testing. And what kind of metrics are we going to use? Well, usually for classification problems, we use so for outcome-based predictions, we use precision, recall, FMS, the classical measures that we use with classification problems, accuracy and AUC, and the higher is better in this case, while for regression problems, so numerical problems, we usually use error metrics like the mean absolute error, the root mean squared error, and so on. And in this case, the lower is better. Of course, we want to minimize the error. And for the prediction of suffixes, especially of categorical values, we use this Dameron-Levenstein distance, which is a distance between the suffix that we have predicted and the actual suffix. And in this case, the lower is better, because we want to minimize the distance from what happened in the reality. Okay, and here I've put some references about all the works that I have talked about in this first part. Are there questions? Okay.
Sorry, I have a question about the page 47. Sorry.
Okay.
Yeah. So I don't understand how to calculate the delta, for example.
Yeah, no, the delta, it's because I have not reported, it's just an assumption. Assuming this is the first event, this is the time between the previous event and this event. So since this is the first one, it's always 0. And here I'm assuming, sorry, I don't report it in the data. I'm assuming that there is 1 hour difference between the previous event and the current event, and here that there is 2 hours of difference between, I didn't say it, 2 hours of difference between the previous event and this event. So let's say this is at 18, the previous one could be at 16.
Okay.
It's just simply that I forgot to tell you,
Thank
sorry
you very
for this.
much.
Okay, you're welcome. Okay.
Thank you so much for your presentation. It was really interesting. I have a question on the same slide, fortunately. Actually, we have a concept of parallelism and choice and loop in process mining. So if there are 2 events that have to be performed at the same time, then what about this vector? How this vector will work if the timestamp is same, like two activities have to perform at the same time, then how it will respond?
Well, of course, you cannot, either you have a start and then end the timestamp, and then you can decide to order the activities based on the start or in the end, according to whether you decide. But if you have exactly the same time, you need to use them randomly, I would say. And yeah, there is no any particular strategy. It's very unlikely that, especially, that it happens at the same time, but it could happen. And yeah, you would just consider it as a sequence. You can decide the criteria for deciding what is the alphabetical order, so that you always keep the same sequence. But I mean, I would not have an answer to this issue, and I don't think that it happens so often that you have exactly the same time. So I would say that on the big numbers, this should not be a big issue.
And what about the loop? If one activity is repeating itself, then the number of vector will be increased, or the counter of the vector will increase?
Your vector will become longer and longer and longer. Yeah.
With the same pattern of activity, like AH. If we have the pattern of 0, 1, 0, 0, 0, so AH will be repeated. If there will be a loop.
You will repeat it, and you will learn that whenever you observe that activity, you somehow have that path. You will learn that pattern actually.
Okay. Thank you so much.
You're welcome.
I was wondering if it's common to use association rules mining as well and sequential pattern mining, or if this classification or like predictive models overcome these methods, and in practice it's better to go directly with predictive models.
Well, I would somehow say that classification methods are more precise with this kind of data than association rules. But this is, I never tried empirically, but this is what, this is my intuition about that. So I would go, if I had to choose, I would go for classification methods also, because you can somehow, you can somehow take into account also with these encodings, they can help you to take into account also some values that possibly with association rules you are not able to correctly or completely grasp, I would say.
Okay, thank you.
You're welcome. Okay, so I will quickly go through just the intuition of these new trends in operational support. I want to say a few words about intercase predictions. I want just because all the encodings that we have seen so far actually look at the execution of a single case, of a single execution. So we are not caring at all about what happens around us. But let's assume that you are at a restaurant and you are having your process, your dinner process. So how long it will take for you to complete your dinner process? Well, if you are alone at a restaurant, maybe it will take a certain amount of time. But if there is only one waiter and one chef, and there are a lot of people, of course, the time that it takes for you to complete your dinner process will be longer. And what if there are some very important persons at the same restaurant that need to be served as first one? So it will take even longer. So the intuition here is that whenever we make predictions, we need to take into account also possibly the dependency between our executions and other executions that are being executed together with us. And there could be different levels of dependency from other executions. We can be alone, and so we do not have at all any dependency. There could be some homogeneous cases, so execution as our execution, so other people at the restaurant like us, but there could be also priorities and other priorities. And the more this dependency is strong, the more information somehow we would need to put in our encoding in order to specify this kind of information. And so the most important thing is that it is whenever there is this intercase dependency, so dependency among cases, we want to encode this information in our encoded vector. Of course, it would be wonderful if we could encode all the information related to all the cases that are running together with us, but as we were saying before, this would make our vector a huge, very, very huge vector. So we need to kind of understanding according to the problem that we are facing, which is the level of dependency, and select the right amount or the right level of granularity of the features of concurrent traces that we are looking at. And for instance, some very simple intercase dependencies that we can consider is how many concurrent simultaneous traces are being executed together with our execution. So for instance, in a time interval, let's say in one day, there are 10 other parallel instances that are running in the same day in which the execution of sigma 1 is running. And so we can report this, and we can also somehow report, I don't know, the average time of these executions which are running the same day in which we are running, because especially when there is competitions, resource competition, this could have an impact on the final predictions that we're going to have. And so having an idea of how many other traces are running together with the trace that we are encoding, or the average duration of these traces could make the difference. Okay, another very short thing I would like to show you is about, okay, so far we have seen predictions, but let's assume that we are in the case in which the doctor wants to know if John is going to recover soon, and our predictive model answers yes. But at this point, the doctor can say, okay, but why this is going to happen? And one way you may know that there is a huge hype in this time on this explainability, artificial intelligence, this Xi approach, and there is a lot of research there. And this kind of research can somehow be applied also to predictive process monitoring problems. And for instance, an idea could be applying these techniques, model agnostic techniques like Lime and Sharp, which tells you what is the impact of a feature on the final prediction, in order to inspect also the data, the predictions returned by predictive process monitoring. For instance, in the case of John, here you can see these bars that represent a generic output of Lime and Sharp, which tells us that, for instance, the pair feature value age equals to 20. So this trace attribute is the one that impacted most on the answer that has been returned by the predictive model, which was yes. And so the answer will be, we are saying that yes, John is recovering fast because he's young, because he's just 20 years old. I mean, it's really just to give you the intuition, and I have reported here just one plot, but there exist also other plots related not to a single execution, but also to the log and to the model. I'm not reporting them here. Just I want to say that, of course, the type of with this kind of explainers, the type of encoding that you use has an impact also on the type of explanation that you receive. So here with the complex index encoding, you have this kind of explanation, but with other kind of encodings, you can have a different type of explanation because the answer of the explainer will be whether the pair feature value is how much or what is the feature and the corresponding value are impacted the most on the final prediction. Okay, then I would like to say something about these predictions when we have some knowledge which does not come from data. So let me make this example. Let's assume, okay, all the approach that we have seen so far, they learn from historical data without any further information, without any context. Now, let's assume that you want to predict the future activities of a passenger at the airport. And there will be, that day, there is a strike. So if we ask to whatever kind of predictive process modeler what are the next activities of our passenger, okay, our passenger take the shuttle, enter via door 3 at the airport, makes the check-in, and then, okay, now what are the next activities? And whatever kind of predictive process model will return you the classical activities that a passenger does in a day in which there is no strike, right? Because it does not know about it. But if we know that, and so, of course, these will be predictions which are wrong because probably the security check at gate 1 cannot be made because there is this strike and the passenger will never leave. So this prediction will be for sure wrong. So the question now here is, if we know that there is a strike, how can we, let's say, tell this to our predictive process monitoring algorithm so that in the end we get more accurate predictions? And well, it's possible. I mean, there exist works in the state of the art that try to guide, let's say, the predictive models towards a solution which is compliant to this knowledge that we can have. So you will have some predictions. You can rank them according to their likelihood. So you could say, okay, this prediction is the first one I would return. And you can check whether it is compliant to the knowledge that you have. Like, for instance, the knowledge that there is a strike. If it is not, you discard that solution. And you say, okay, let's try with the second most likely suffix that I can predict. Okay, this is not compliant, I will discard it. And you will keep only the one that is compliant to your knowledge. And this is the one that you are going to return to the final user. Just really, I wanted to give you the intuition, and you can do this by, let's say, exploring the next steps, and whenever you reach, so for instance, you are at time M, you explore all the possibility, well, let's say a limited number of possibility, let's say 2 branches at step M plus 1, and then you move to step M plus 2, and you go ahead like this until you reach an end state, which is marked here with a double circle, and at this point you check whether this is compliant with the solution, and if it is not, you kill this branch and you continue exploring your next activities until you reach a solution which is compliant with your knowledge. Okay, last, just really again the intuition. Predictions can be used also, as we said at the beginning, for making recommendations. So for suggesting what is the best action to do in order to achieve a certain goal. Here the idea is very similar to the one that we have seen for predictions, but this time we are going to return at runtime a recommendation on what to do. So for instance, do this or do that. And yeah, we can recommend the next activity, the best resource, the routing decisions, and always we usually have a goal, or a business goal, or a measure of interest that we want to optimize. Like for instance, we could be interested to minimize the remaining flow time, to minimize the costs, to maximize the fraction of cases that is accepted, and so on and so forth. And I don't know if I want to give you really the intuition about how to use predictions in order to make recommendations. So let us assume that we want to recommend the best activity which allow us to minimize the execution flow. And so one thing that we can do is to look at the next activity, to try all the possible activities that we can recommend, and try to predict what will be the remaining time. The remaining time if we execute activity, for instance, A1, and what will be the remaining time if we execute activity A2, and what will be the remaining time if we execute activity AN, and so for all the activities. And then what we are going to recommend, we are going to recommend the activity which allows us to achieve, to have a predicted time, a predicted remaining time, which is the lowest one. Okay, so this is more or less the idea. And you can do the same also if you have another type of business goal. For instance, if you want that John recovers soon, you can look at the states, at the different activities that you can do as next activity, and you can have a look at, you will discard the cases in which John is not going to recover, so the state one in which the recovery of John, the prediction of the John's recovery is no. And so you will discard that one, even though it is the most likely one, and you will keep the one which brings you to a prediction, which is, yes, John will recover, and with the highest likelihood to happen. And so in this case, we are going to recommend perform ultrasound because it's the most likely state that we can reach such that John is going to recover. Okay. Okay, and I have put also here some references. And if there are no questions, okay, maybe I can just quickly go through the tool support, and then I can save 5 minutes for questions, okay? So, tool support, I want to say that there are several tools which allow you to make predictive process monitoring. In PROM, you can find several plugins, both related to model-based approaches and machine learning approaches. In Apromore, you can also find plugins which allows you to make predictive process monitoring. And then the last one is Nirdizzati, which is a dedicated tool for predictive process monitoring. And I would like just to spend a few words about Nirdizzati. You can find the link here. Also, well, Nirdizzati, first of all, is a Sanskrit word, which means prophecy or premonition. And what is the idea of this tool? Well, the idea of this tool is that it allows a user to train several different predictive models with different machine learning techniques, with different encodings, with different type of bucketing, and then it allows you to evaluate and compare these different models. And so that you can select then, in the end, the ones that is most suitable to your needs. And as I was saying, it's a kind of, we can consider it as a kind of meta tool of predictive process monitoring, because allows you to compare several different predictive models. So you can try several different combinations. You can see the results on a particular log, on a particular subset of your log, and then you can choose what is the best machine learning technique or the best, encoding for your specific problem at hand. You can find the screencast at the link. I will just, maybe I can go through the slides so it is faster. So you will find an interface like this one, and there are seven steps. You can either upload your log, you can find the log details, you can split your log, you can look at the label distribution. So if you have a log and you want to test whether, for instance, what is the distribution of true and false, you can use this labeling page. You can then train your models. You can check, the status of the task, and you can validate them. Let me just show you. Okay, this is the first page where you can upload your log. You can either upload it one log, or you can already upload it separately, the training, and let's say here we call it validation because we want to validate on several different models, but it's your test set. You can have a look at at what are the, for instance, the number of events in your log, the number of events per day, and the number of resources per day, and the number of new traces started per day. You can also, if you upload a unique log, you can decide to split it. And actually, here in the splitting method, you can choose the type of splitting. I mean, if you want to split the data set ordered with the temporal order, with the strict temporal order, as we said before, or if we want to just split it randomly. You can here, as I was saying, you can look at the distribution of the labels. For instance, in this case, there was a label, and in 546 cases, the label was false, and in 80 cases, it was true. Of course, when you have unbalanced data sets, the predictions could be less correct, so it could make sense to inspect also the distributions of the label. And then you have a huge set of things you can use for configuring your training. You can select whether your problem is a regression problem, a classification problem, or a time series problem. And for each of these groups, you have different classification methods, and you can check more than one of them. And you can also to encode, to check different types of encoding. And yeah, and then you can look at the results in the validation page. Now I'm just since we do not have so much time, I just want to tell you that, let's say, in the validation page, you can make a comparison among all these configuration of predictive models that you have trained before, and you can identify the one that is the most suitable one for your data. So for instance, okay, here there are several different configurations. So here we have trained random forest, XGBoost, SGD classifier with different types of encodings. And here it seems that, okay, this blue one, SGD classifier with complex encoding is not performing very good in terms of F-score, while there is the orange one, which is the XGBoost, which is the simple index, is performing good. You can also choose different prefix lengths. And yeah, here there is an average visualization. And you can also inspect the different things case category by category. So for instance, you can look at the classification method. For instance, there, the SGD classifier. So here we want to have, since on the x-axis we have the F-score, on the y-axis we have the AUC. So, so we want the best results are the bubbles that are at the top right angle. And so in this case, the SGD classifier is the one performing worse on different prefixes and on different, on different prefixes actually, while the XGBoost and the random forest are the one performing better. I mean, you can inspect different dimensions through the tool. Okay, maybe I want just to say that if you want to play with the tool, you can find the version online. Plus, in the summer school website, there should be a version for the local installation of the tool, if you want to do it. And there is also a link to a form if you want to fill it, a form on predictive process monitoring and on this specific tool. And I think that's it. I will conclude. So, and then we have 5 minutes for questions, I guess. So we have seen what predictive process monitoring is. We have seen the main state-of-the-art related to predictive techniques, approaches related to predictive process monitoring, and the main encodings that are used in the state-of-the-art. And we have seen that we can compare and evaluate different types of techniques and configurations so as to identify the best ones. And I would say that predictive process monitoring is, especially the new trends, is a field, and there are some fields that are keeping growing. So I think there is a space for a lot of research on this. And I would just say that I would like to thank you, all the people that I have listed here, because they have contributed to the material of this, to the content of these slides. And that's it. Thank you.
Chiara, for your nice presentation. Yeah, we have still 5 minutes for further questions. Yep.
Thank you. Okay, I would say no, I have never tried. I would say one answer is we do not have here the process model, the de facto model, so all these techniques now work only on, the ones based on machine learning techniques work only on the data, and so we do not have the, let's say, the correct model that so we cannot measure the non-conformance. Of course, if we had that, could be interesting to also measure possibly the non-conformances and to add a feature related to fitness to a model that could be, I think, very, very useful, because it could easily tell you, how far is your execution from the standard executions, and could be maybe also useful in the case in which we have a specific context of, noisy traces that could be also very useful. But I think, and this is one part of the answer, and the other part is that instead, if you don't have the model, I think that it's correct also to, as I was answering to somebody else before, it's correct to also make predictions of deviant cases, let's say, even if they are not correct, because that in the recommendation phase could help you in. But yeah, of course, if we had the model, that could be an interesting thing to look at. I agree. Okay.
Thank you for the presentation. I have a question, the same related to the process model and the prediction model. So if you use the same data to create a process model, and then you use that data for making a predictive model, could you use the process model as a kind of way to explain the predictions of the predictive model if they come from the same data source?
So you mean you discover a process model, and at the same time you train a machine learning model in order to make predictions? Well, maybe for some predictions it could help, but I would say that this kind of explanation would help much more with the predictions done on these explicit process models, because there you have a mapping one-to-one, as we have seen before. If you have an explicit process, you discover an explicit model, and then you try to make predictions over that model, I think, of course, the mapping will be one-to-one. With the machine learning approach, I don't know whether, well, I think that for some predictions it could help, but not for everything, especially the ones, for instance, specifically related to data. Maybe it would be difficult to find the connection between the discovered model and why a certain prediction has been returned by a machine learning model. But maybe if you only consider the encoding based on the control flow, so you give a prediction only based on the control flow, maybe that could be helpful. Of course, as usual, which is, I think, somehow also related to these non-conformances, the noisy or the behaviors that are not captured by your process model could maybe be captured somehow by your machine learning model, and so for some of the predictions possibly you cannot have a so clear explanation, but for most of them possibly yes, if you look only at the control flow.
Thank you.
Okay, thank you very much for the insightful presentation. Actually, I have several questions, but I can ask only one right now. Everything you said about predictions, either for outcome or remaining time, numerical values, the focus was only about predictions, the quality of predictions, the accuracy of predictions. But what about the uncertainty associated with the predictions, especially if we are going to recommend a specific action to unhappy customer, let's say? So how to handle an uncertainty that is attached to the predictions, either for outcome or remaining time?
Okay, okay, there are, whenever you use a machine learning model, you somehow have also a measure, together with the prediction, you have somehow also a measure of confidence of how, well, especially, yeah, of confidence, or as you said, yeah, the opposite way, no? Not the uncertainty, but the confidence that you have in the prediction that is returned. So yeah, that could also be an interesting thing to not only return the predictions, but also the confidence that you have with respect to that prediction. And this is, as you were saying, especially true in the case of recommendation, because as in the example that we have seen, you could, for instance, assuming that you want to recommend what is the best action to take, maybe there are several actions that leads to for instance, John's recovery soon, just to make an example, but you would probably try to recommend the one for which the predictions of John's recovery is the most likely one. So the one for which you have most the highest confidence, and so the less uncertainty towards that prediction. So I think, yeah, it is an interesting thing that could be explored also in just one returning predictions. That could be interesting, yeah.
Okay, thank you. So also thank you from my side. I get to ask the last short question. So I was wondering if you think it would be worth it to look in the indexing not only at left align, because right now if we're indexing by appearance in the trace, we have this left alignment. If it would be worth it, if we're looking into a certain activity or a certain event that always happens towards the middle, always happens in a certain index, to look at this aspect, aligning it into that position or into a heat map of that position.
Yeah, I think that there are still methods related to the encoding of the traces that have not yet been explored, and I think that this could be one interesting one, and yeah, I think that could be, or for instance, patterns that occurs or not occurs, and this could also, yeah, I think there are still methods that could be explored for the encoding, and maybe also trying to understand what is the best encoding with respect to your data could also be interesting. So yeah, I agree. Thank you.
This will conclude the session. Another big applause for Claudia.
Thank you.